So in terms of when we do labs versus the material, I see an advantage to either way of you make sure you cover the material first and then you do the lab, or you do the lab first or partway through the material and then finish up the material. Do you have a preference?
I mean, I kind of like knowing it before going in.
Okay.
Just have that kind of
I'm
knowledge.
kind of new. I'm okay with either one or the other. A little bit leaning on what he said though about doing it, about learning it first.
Okay.
I would agree.
Okay. And most students feel that way, but to me, the other way, it has sort of an air of mystery of why is this working? And then you get to class and go, oh, that's why it's working. Oh,
Now that when you say it like that, yeah, it does, I can see why some people would go towards the other one.
yeah.
Yeah, I'm either or.
Okay. So the Vibrating String Lab, then we will do a week from today, as opposed to Monday.
You mean with that, that's what we did, that's what we did on Monday, right?
Yeah, I did the demonstration of it. You'll do that lab.
Oh, okay.
So let's see, 131. Today's 27th, so, and then do vibrating string lab. And the simple harmonic motion labs are due today.
Oh yeah, turn on in Monday.
Okay,
Do today or?
I thought I turned mine in already.
that's possible.
Yeah.
Yeah, you had there was
That's Hook's Law,
Yeah.
Hook's Law lab.
Hook's Law.
Oh,
Simple harmonic motion lab is.
I am really screwed up with time now.
That's okay.
I'm gonna blame COVID on it, but I was answering emails and I thought, oh, okay, I got class at 12:30. And then I was looking at emails and going, I haven't responded to emails since Tuesday? What have I been doing for the past 2 days? And then it hit me, oh, it's Wednesday.
Yeah.
I have class at 10. And then I was just looking right there, acknowledged that today was the 27th and suddenly thinking it's a week later. But at least I'm recording this so that future people will look at, well, here's where you can start to see the signs of mental degradation. So, seems like there was another bookkeeping thing. Oh, I have a student, one of my online students is trying to find a time when we both can meet. 10 o'clock would have been perfect for him, but obviously I'm with you. The plan is somewhere around 10:30, I'm gonna get you started on the lab, and then I'm gonna meet with him in my office. So if you have questions, please interrupt. He's aware that I've got class going on or lab going on, but that is the plan. If I'm gonna be in the other room though, you cannot die. Because that's a lot of paperwork for me and explanations of why I was not in the room at that time. So, can you at least promise me that you will attempt not to die during the lab?
Absolutely.
Absolutely.
Okay. Also, at some point during the lab, I'm gonna hand back the quiz from chapter 13 as well as the Hook's Law lab. So, when I do that, don't just drop everything to look to see what I'm handing back to you. Wait till an appropriate moment. If you all agree in your group that, you're gonna take a break to look at what was handed back, that's fine, but don't stop in the middle of it and mess everyone else up. And it's also possible I will forget. That's not a sign of mental degradation, that's just who I am. So. Any questions before we do a little bit of content? Then let's talk a little bit of content. So if you imagine back out there when I had we were working with the long coil, and I started moving the coil back and forth, hand moving in sort of sinusoidal motion, producing a wave that ultimately would propagate down that way. There's some central point here. And if my hand is moving back in sinusoidal motion, or like a sine wave or a cosine wave, then we can think about a point of mass right here moving back and forth like a sine wave. In other words, we can model it with simple harmonic motion. So if sinusoidal motion, then assume simple harmonic motion. And suddenly all those rules that we did with simple harmonic motion in the previous chapter, or in chapter 14, previous chapter, apply. So if we think back to a spring, I have some equilibrium position here, and then I pull it out a certain distance and I let go, and it's going to oscillate back and forth. Energy is conserved. So I know that kinetic plus potential energy is equal to some constant. E sub m for mechanical. And so if I pick a convenient spot, such as out here, when it's not moving, so I pulled it out this far, I let go, the speed is 0, so my kinetic energy is 0. So this would be equal to my maximum potential energy, which is 1/2 spring constant x squared. And that would also be equal to the kinetic energy at this point, 1/2 mv squared. So this would be the maximum displacement, and this would be the, I guess technically there's a delta there, and this would be the maximum speed. So in essence, all I'm doing is looking at treating this like simple harmonic motion, and then figuring that it's has 0 speed at this point, because that's the turnaround point, and maximum speed at this point. And I've just done it horizontally. Well, if we think about that sinusoidal motion, my position can be described by some amplitude times sine or cosine of omega t plus the phase. Flashback a couple classes ago. My velocity is some a omega negative sine omega t plus phi. And my acceleration, negative a omega squared cosine omega t plus phi. And again, this should not be new. But if we look at that, that's my maximum speed right there. Whatever the amplitude is times omega. So my total energy is, or my total mechanical energy, is 1/2 times the mass times my maximum speed times omega squared. Now the textbook takes it one step further. They, instead of using the angular frequency, they prefer just the normal frequency. In other words, f. And we know that omega is equal to 2 pi f. Again, going back to chapter 14. And so plugging that in here, we have our total energy now is equal to 1/2 mass times a squared, because I don't need parentheses at this point, times 2 pi f squared, which is 1/2 mass times a squared 4 pi squared f squared. that 1/2 and the 4 become a 2. And so I end up with my energy of that wave, or the particle part of the wave, is ma squared 2 pi squared times the frequency squared. Because the mass is being distributed, we're not necessarily looking at just a tiny little bit of mass there, we're looking at mass of the whole thing. So, however, the mass of the whole thing is not necessarily simple to deal with. We tend to work in terms of linear density here. If you recall, linear density is mass divided by length. So basically going to divide both sides by length. Right there, I got my linear density. And so we now have an expression for the energy per unit length of this wave. It's going to be, I guess traditionally the numbers come first, 2 pi squared a squared f squared mu. It's equation 21.5. And we can take that next step. Power. And I'll bring it to you. What is power?
Okay, full times what?
Oh, no, both times.
Oh, that's all I said.
Sorry, what'd you say again?
I was doing engineering power, not.
Or electrical power.
Electrical power, yeah, mechanical power. And the electrical power derives from the same thing.
I don't remember that.
It's like wattage times. Oh, it's like, no, I'm thinking of conversion, never mind. Powers in watts.
Mass times speed, velocity.
Wait, say it again?
Mass times velocity.
That would be momentum.
Oh.
At a different P. Suppose I were lifting this ball right here, and I did it really slowly. Ooh, just in case you couldn't visualize what lifting something slowly was. Versus lifting it quickly. Which took more power?
Faster one.
Right. The faster one took more power. The same amount of energy was spent in both cases. Because I'm taking the ball from here to here. I increased its potential energy. I did work in order to do that. If I lifted it to the same height, I spent the same amount of energy. The difference was the amount of time it took. So power is basically the energy that was spent per time. Crudely, just energy divided by time. We can throw some deltas in there if you want. Sometimes it's work divided by time, but there is a relationship definitely between work and energy. And if we're looking at time here, then let's go back to distance. Or actually do speed. Speed is distance divided by time. So if I have a rope that has a certain length, L, then my time is going to be the distance traveled divided by the speed of that wave. So this becomes energy over distance over speed, which is energy for length times speed. Hey, we just happen to have a formula for energy per unit length. And an eraser over here. So this would be 2 pi squared, the amplitude squared, frequency squared, mu times z. Ooh, these two equations are almost one-offs. Doesn't really fit into the flow, I think, as well as some of the other equations, but I at least wanted to get that out there. And one other thing I wanted to cover before we start on the lab. Any questions up to here?
Is the unit still watts?
Yes, the units should be. Let's just double check. So we're talking about a physical rope right there being lifted up. This becomes 2 pi squared. So unit wise, this would be meter squared. Frequency is hertz squared or over seconds squared. Mu is a kilogram per meter, and speed is a meter per second. And so we are left with, that cancels out with that one. Well, I guess I could have done that one. But we have kilogram, meter squared per second cubed. And a kilogram, meter squared per second squared, times 1 over seconds. That's a joule. So that's a joule per second, which is a watt.
Oh, okay.
It's usually easier to think, all right, I'm dealing with SI units and making sure all my masses are in kilograms, all my distances and so forth are in meters, time is in seconds. And so, yeah, it's power. It's going to be watts in the end. But occasionally it's nice to remind ourselves, do a quick dimensional analysis to find out if we went astray somewhere. Other questions at the moment? All right, sort of changing gears slightly, we're still dealing with the standing wave, similar to what we did out there where we talked about the harmonics. So if I have 2 fixed ends, and the ends are a distance L apart, the simplest wave we can produce, at least mathematically, the simplest wave is that, where I've got fixed ends are nodes.
Yeah, you said that's first order.
Our first harmonic.
Oh, right, yeah, first harmonic.
And how many waves is that?
That's a half a wave.
It is indeed a half a wave, because the full wave goes up, down, and then back up again, and so that's a half a wave. So my length is equal to a half of a wavelength, or my wavelength is equal to 2 times whatever L is. I know that the speed of the wave is equal to the frequency times the wavelength. And since my wavelength is 2 times L, this becomes frequency times 2 times L. So it depends on what you're trying to find here. I'm just going to do it frequency for now. Frequency therefore becomes the speed of the wave over 2L. If we're talking specifically about some linear medium, like a string, then we have another equation for the speed. This would also be equal to 1 over 2L times the square root of the tension over the linear density. And we can manipulate and play with that, but that's the essence of sort of where we're going on this. If I do my second harmonic, well, the two ends have to be fixed because it's two fixed ends. The two ends have to be nodes. So it looks something like that. It should be symmetrical if drawn properly. How many waves is that? So L is equal to the wavelength, or the wavelength is equal to L. Third harmonic?
1.5.
Yep.
So for every harmonic, you get one. For every 2 harmonics, you get an extra wavelength.
Yes.
Okay, just want to make sure.
There's, for this case, absolutely. For the two free ends, absolutely. For one fixed, one free end, the language needs to change a little bit. The spirit of what you're saying applies to all three of them. However, when we get to one fixed, one free end, there's the first harmonic, the third harmonic, the fifth harmonic. The even harmonics don't officially exist.
So, and that's when there's just one fixed end.
Correct, one fixed, one free. And so whenever you go to the next legitimate harmonic, you're gonna add a half wave. If you go every second harmonic, every second legitimate harmonic, it's adding a full wave. That would be more precise language.
Oh, okay.
And I'm sure there's some videos out there where I'm saying something a little bit different because I've changed my language a little bit over the past couple of years. All right, let's do two free ends. Free end, node or antinode?
I would say antinode.
Well, yeah, it would be an antinode because as it moves on the free end, it's gonna hit the maximum amplitude.
Absolutely. So what would the simplest look like? Somebody want to do a hand gesture for what the simplest, the first harmonic would be?
What's the fixed point?
Because you got two free ends.
Yeah.
Like this?
Okay, I was thinking different hand gestures, but sure, we can go with that. And I find that, so basically I was picturing this, I don't remember. As opposed to, I guess you did that and you did that. I'm gonna try to draw that a little bit better, so I will turn my back on you.
Yeah, I was visualizing I was just visualizing the points moving.
So if that distance there is L, and this is again the first harmonic, how many waves is that?
Still just.
Still just a half a wave because it's from antinode to antinode.
So it's like you're looking at the full wave here, but you just chopped off the outside quarters. So the length is equal to a half of a wavelength. It's the exact same math as right there. If I go to the next harmonic, probably one of my best sideways drawings I've done. That would be a full wave. It's just that we have two free ends instead of two fixed ends. Now, what exactly physically would two free ends look or sound like? How could I produce something with two free ends? Because the two fixed ends we demonstrated already. 2 free ends. That's the second harmonic. Third, fourth, fifth. Here's the first harmonic. Yeah.
Silence.
It's so silent, I can't hear it.
But we nailed it perfectly. We'll make a prediction and we will nail that sound right there. Next week we'll actually go through. Unfortunately, it probably got caught on camera.
That would be good.
Next week we will go through and we will predict what the frequency of sound is, and then we'll see how close we get. Then 1 fixed, 1 free end. When I draw it, a fixed end is node or anti-node.
No,
And free end,
it's anti-node.
and that's the simplest one, that's the first harmonic. The next simplest, again, I'm gonna add a half wave each time. So this first harmonic here, how many waves is that?
Still halfway.
No, it's not a half,
A quarter of a way.
it's a quarter. Because you're getting rid of
Oh, I
3
see.
quarters right there.
Yeah.
So L, assuming this distance here is L, is equal to a quarter of a wave. How many waves is this?
Half. Wait, no, because you got that 3/4.
Yep. So this officially is the third harmonic. In the test that I posted online, I probably need to make sure I go through and adjust the language, because I called that the second harmonic for the longest time, because it's the second one, when officially it's really the third harmonic. And that would look like, there's one back there, there's one over here. This is where we can produce the 1 fixed, 1 free end. You put water in the tube here, sound is we'll take a tuning fork over the top of it, the sound waves will come down, they'll bounce against the water or the fixed end. We have a free end up here, which is open, and so we can produce these harmonics here and actually use it for predicting the speed of sound. And it comes out reasonably well, assuming that you identify correctly where the harmonics are. There are a couple of false harmonics on this one that can really throw off an experiment completely. All right, I was gonna end it here to get you working on the lab. So we need shields, face shields,
Yes, please.
and the slinkies are down there. The supports are here, and some were actually put together already. Feel free to use whichever.
I'm gonna run to the restroom.
That is not your group. Oh. Aaron, Holden, and you have yours. Holden. Hey, Aaron. Gong.
Thank you.